Every phone call, every message begins as a physical event, a human voice vibrating air, creating pressure waves that travel outward in real time. Inside the microphone, pressure becomes electrical energy. This analog signal, a continuous wave, is defined by peak height, amplitude, and cycle length, frequency. Looking closely, the amber wave has no gaps or steps. Between any points exist infinite voltage values. It perfectly mirrors the original sound. But this absolute faithfulness is also a distinct liability. Because the analog wave is inextricably tied to the physical world, it is completely exposed to the physical laws of the universe. Every force it encounters will leave a permanent mark. For this voice to reach a friend's ear in another city, it has to cross hundreds of miles of copper wire, optical fiber, and open air. At the edge of the device, two potential communication pathways stretch out toward the horizon. On the left, a hazy, continuous analog circuit. On the right, a highly structured, precise grid of digital logic. The exact same voice will travel both roads, but only one of these systems is designed to strip the message of its physical vulnerability entirely, allowing it to survive the journey intact. We begin on the analog path. To travel long distances efficiently, the low-frequency voice signal hitches a ride on a high-frequency carrier wave. An amplitude modulation, the voice signal modifies the amplitude of the carrier, shaping its outer envelope to match the spoken words. As this wave travels through the physical medium, it loses energy and shrinks, a process called attenuation. At the same time, the random motion of electrons in the wire generates thermal noise. These chaotic electrical disturbances attach themselves directly to the waveform, distorting its precise shape. To counter the fading signal, engineers place amplifiers along the route. The amplifier boosts the entire signal back to its original power. But it cannot distinguish between the intended message and the environmental noise. Everything is amplified together. With every mile traveled and every amplifier crossed, more interference joins the wave. By the end of the line, the accumulated chaos of the environment is permanently baked into the original message. Now, we reset to the start and take the second path. Here, the voice enters an analog to digital converter. The first step is sampling. Instead of sending a continuous wave, the system takes discrete snapshots of the wave's amplitude at regular time intervals. The Nyquist-Shannon theorem dictates that by taking these snapshots at a rate exactly twice the highest frequency of the voice, the system captures all the necessary information to rebuild the wave later, without missing a single detail. Next, these exact continuous measurements are forced onto a fixed grid. This is quantization. Each sample is rounded to the nearest available voltage level. The tiny difference between the true value and the grid level creates a marginal quantization error, but it establishes a finite set of strict mathematical states. Finally, through pulse code modulation, those specific grid positions are translated into a binary code. The physical wave is gone. In its place is a pure stream of ones and zeros. By sacrificing the infinite resolution of the physical wave, the system gains mathematical certainty. This binary stream is then chopped into addressed packets. In a packet-switched network, each block of data dynamically navigates the maze of the internet, finding its own independent route to the destination. This is a stark departure from legacy circuit switching, which required operators to manually lock open a continuous, dedicated physical wire between two callers for the entire duration of their transmission. Out in the network, the digital signal faces the same physical realities as the analog wave. The binary stream does not magically repel interference. As it travels, thermal noise attaches to the pulses, warping their rigid, geometric shapes. But instead of blindly amplifying the corrupted signal, the digital network uses regenerators. A regenerator evaluates the incoming voltage against a fixed decision threshold, asking a single question: is this value high or low, 1 or 0? As long as the noise hasn't pushed the voltage across that center line, the regenerator outputs a brand new, pristine pulse. The accumulated noise is simply discarded. The system reads through the physical damage, rebuilding the objective truth of the message from scratch at every checkpoint. Even when severe interference manages to flip a bit from a 1 to a 0, the network relies on error correction codes. By embedding extra parity bits into the data stream, the system creates mathematical insurance, allowing the receiver to pinpoint the exact location of a corrupted bit and immediately flip it back to its correct state. The architecture of this resilience traces back to mathematician Claude Shannon. In 1948, he established the foundational laws of information theory, proving the absolute maximum capacity that any communication channel can carry under the presence of noise. The problem of long-distance communication was no longer a matter of fighting physical degradation with thicker cables or larger antennas. It became a battle fought with advanced mathematics. After crossing the network, the digital packets finally arrive at their destination. Here, they enter the digital-to-analog converter to begin the journey back into the physical world. The binary words are decoded back into specific voltage levels. Each voltage is held constant, building a rigid, staircase-like approximation of the voice. Passed through a reconstruction filter, the high-frequency artifacts are suppressed, smoothing the jagged staircase back into a fluid, continuous wave. The abstract numbers are translated back into the exact physical pressure required to drive a speaker and push the air. As the recipient presses play, the two versions of the message arrive. The analog path yields an audio signal degraded by accumulated static. The digital path delivers a crystal-clear reproduction, identical to the moment it was spoken. While this digital reproduction feels perfect, it remains bound by the Shannon-Hartley theorem. No matter how sophisticated the encoding, the ultimate speed and capacity of this transmission are strictly limited by the available bandwidth and the fundamental noise floor of the universe. And despite the elegance of the math, these numbers still require heavy physical infrastructure. They rely on vast arrays of submarine cables, fiber optic backbones, and colossal satellite dishes to bounce the binary data across oceans and into orbit. Every second, billions of these discrete conversions are taking place globally, firing across a vast, invisible digital grid. By translating physical reality into the discrete language of mathematics, we bypass the inevitable decay of the natural world, compressing the entire planet into a single connected room.